This little video is going to talk about the unit circle and trig ratios. First of all, we need to know how to convert from degrees into radians. We know that one full rotation of a circle is 360 degrees. In radians, one full rotation is actually 2 pi. So we're going to use this fact to help us use our conversions. For instance, if we set up equivalent ratios where we put degrees and we make them equivalent to our radians, which right now we do not know, and we set it up so we have the ratio that's related to 360 degrees for one circle and 2 pi in radians. This keeps all of our degrees on one side is equivalent to our radian measures here. Now we can cross multiply and reduce, and you can also set up your fractions in the reverse order with the 360 on the numerator and 45 on the denominator, as long as you have what you have and what you want as numerators or denominators. And then we can cross reduce, just like so. So as you can see, I can reduce down my degrees. I can cross multiply to get this, and then I can isolate for x and reduce. 45 degrees is equivalent to pi over 4 radians. Another fact that you should know about is the arc length equation, which is really based on why radians exist. Radians exist because it is a unit of measure where the radii between the two arms, I should say, of the angle, which we'll call r, is equivalent to the arc length. So one radian has two arms that are equivalent to the arc here that all measure r. Based on that definition, it's based on the idea of circumference, and the arc length is basically, in radians, a portion of the radius. Coterminal angles are basically angles that share the same terminal arm. We've talked about positive angles and negative angles, ones that go counterclockwise and one that goes clockwise. So there's a difference between the positive angles and the negative angles. These two angles share the same terminal arm. They have the exact same position within the Cartesian plane. We can also have multiple rotations with this little bit extra here that is equivalent. This also has the same terminal arm, but it has a different value for the number of rotations that it goes around. As you can see, if it goes around once, we're going to have basically, this is equivalent to 2 pi, one rotation, plus our first theta that we had there. This one here, because we're going negatively, 2 pi is all the way around. We're basically going from our angle, we're subtracting 2 pi off of it. So this angle is equal to our theta 1 minus 2 pi. So you can see that all these angles that have the same terminal arm are all based on multiples. If I went around twice, I'd have a 4 pi. So they're all based on multiples of 2 pi, adding or subtracting 2 pi to your initial angle in standard position. Now it's also very useful to know about special triangles and how the unit circle is related in terms of radians. So we know about the 30, 60, 90 triangle. In radians, we have pi over 6, pi over 3, and pi over 2, which is our 90. And our ratios are going to be 1 to root 3. For your reference, this is 30 degrees, a smaller angle. This is a larger degree, 60 degrees. But you should know them in radians as well. For the 45, 45, 90 triangle, now we're going to refer to it as a pi over 4, and of course pi over 2. And it also has the same ratio as before, the 1, 1, root 2. The unit circle helps us with a few of the other angles as we go around that we don't necessarily use triangles for, but the unit circle helps us to visualize. We know that these angles, 0, 90, 180, 270, and then all the way back around for 360 can be written in terms of radians as I've written them there. Each of these on the unit circle have a coordinate point. These coordinate points help us identify sine, cosine, and tangent values. This coordinate point here, because it's a unit circle, the radius is 1, so this point here is 1, 0. This point here is 0, 1. This one here, we have -1, 0, and down here, this coordinate point here is 0, -1. Now, based on the concept of opposite over adjacent and your opposite over hypotenuse, all those ratios for sine and cosine, it actually ends up that the first coordinate is going to be your cosine of 0, or you can say the cosine of 2 pi if you went around the circle twice. And the second coordinate here is going to be your sine coordinate, so sine of 0 or sine of 2 pi. Same thing as you go around the circle. This one here now is your cosine of pi over 2, and this one here is going to be your sine of pi over 2. Down here, cosine of pi and sine of pi. And the last ones as well, cosine and sine of 3 pi over 2. Now that gives you the sine and the cosine. You can, from this as well, look at the slope of each of these lines. That represents the tangent, mainly because you have your opposite over your adjacent, which is the same idea as slope. My slope here, my rise is 0 and my run is 1. So here, my tangent value is 0. Here I have a vertical line. So, vertical lines, we also know that the slope is undefined. So tangent of pi over 2, undefined. So in terms of the graph for tangent, it will have an asymptote at this point. And as we go along here, here's another slope here of 0, and then a slope that is undefined as well. Another thing we're going to be talking about is the equation of a circle and how to use this equation. The basic equation of a circle is actually based on the idea of the Pythagorean theorem. Here we have x squared plus y squared equals r, where r squared becomes your radius squared. So if I had a radius of 4, that would then create a circle equation of x squared plus y squared equals 16. Now this equation of a circle, also you must note that this one has a center at 0, 0. There's been no transformations on this graph, so the origin here is the center 0, 0 with a radius of 4. Now this will come in handy either thinking about it in terms of Pythagorean theorem, because you can basically make little right angle triangles and look at that here to figure out what the coordinate point is going to be based on the radius. If you knew one of the x's, you could then figure out what the y value would be as a result if you knew what the radius was. So particular examples of this would be when you were looking at a point based on a particular angle. So if you were interested in this point on a unit circle, this will give us then our angle that we're looking at, and it's going to give us a coordinate point based on the cosine of 3 pi over 4 and the sine of 3 pi over 4. Like we were just talking about before, we can evaluate those two values based on the angle, being that it's in a unit circle. Other scenarios is you might get the actual point, and you may have to work backwards. If you know this is a cosine, you can then determine what the angle is, and then in turn find your missing coordinate. So we're going to look at trigonometric ratios, all 6 of them. So sine of theta, cos of theta, tan of theta, you've probably talked about in terms of opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent. We're going to use the terminology y over x and r for radius, which is our hypotenuse. So sine of this angle is going to be your opposite over hypotenuse, so y over r. Our cosine is our adjacent over hypotenuse, so x over r. And our tangent is our opposite over adjacent, which is y over x. Now cosecant, secant, and cotangent are the 3 other trigonometric ratios. They are the reciprocal ratios, which means that cosecant is 1 over sine of theta, secant is 1 over cos of theta, cotangent is 1 over tan. Because they're reciprocals and we're working with fractions here, numerators and denominators basically switch. So we can write this also as r over y, r over x, and x over y. It is important also that you know about the quadrants. Every quadrant has a few different little properties in terms of their sine and their cosine values. The quadrants go around counterclockwise, 1, 2, 3, and 4. In quadrant 1, the x and the y values are all positive, and any slopes that we have are positive. So we refer to A, meaning all, are positive within quadrant 1. In quadrant 2, we have negative x values and positive y values. That automatically makes all the tans become negative because you have a negative divided by a positive. Here, for the sine and the cosines, it ends up that sine is going to be the only one that is positive in this quadrant, and cosine is the one that will be negative. So we refer to this as the S quadrant, that sine is the only one that is positive. In quadrant 3, same idea, we look at our x values and our y values, both of which are negative, and our slopes, a negative divided by a negative will give me a tangent value that is positive. The other two, as a result, are going to become negative. In quadrant 4, again, our x values are positive, our y values are negative, and if we look at the ratios for each of these, cosine ends up being the only one that is positive. As a result, when we are doing some of our calculations, we will end up with two quadrants that they may actually be the same sign. Tangent is negative in both quadrant 2 and 4. Cosine is positive in both quadrants where 1 and 4. So you will always end up having a pair of quadrants where they have the same output in terms of their ratios for that particular value.